A lot of text in this exercise, but what this basically is all about is about a two-dimensional square lattice of dielectric rods. So here you see that lattice in top view. So this is your photonic crystal. And then there can be two situations. One where the electric field is lying along the rods, so parallel to the rods, or a different situation where the electric field is perpendicular to the rods. So let's just draw these two situations in a bit more detail. So when the electric field is parallel to the rods, if you now have a look at the cross section, so this is a single rod here. If the electric field is parallel to the rods, you get the following situation. This is what's typically called TM polarization in photonic crystal parlance. Whether something is called TE or TM depends very much on the reference plane you choose to be transverse with. If you choose a different reference plane, like what people do in waveguides, for example, you might end up calling something differently. But in photonic crystals, if the electric field is parallel to the rods, like in this case, that's called a TM polarization. So that's one situation. Another situation that we can have is where the electric field is perpendicular to the rods. And then our diagram looks something like this. So these are the different electric fields, either inside or outside the rods. And this is called the TE polarization. Now we're going to assume that the rods have a refractive index which is higher than its surroundings. So this means that epsilon 1 inside the rods is actually bigger than epsilon 2 outside the rods. So this was the background. What we're now trying to figure out is if we look at the electrical energy on both sides of the interface between the two media here, will you have the situation that the electric field is more concentrated inside the rods or in the air between the rods, depending on the polarization. So what we need to calculate is the electric energy. So let's call that W, because we already used E for the electric field itself. So the electric energy is, of course, epsilon the modulus of E squared. So your goal is to calculate W either just inside the rod or just outside the rod for the TM case and for the TE case. And then draw some conclusions based on that with regards to the confinement of the field inside the rods. So pause the video and try to do that for starters for the TM case. Okay, let's do the TM case. Let's redo our drawing. So for TM, we have the following situation. We have the electric field inside the rods, that's E1. And then just on the other side, we have the electric field outside, that's E2. Now we know from basic electromagnetic theory that if you cross an interface, that then the tangential part of the electric field is continuous. Now, if the tangential part of the electric field is continuous, that means, translated to our situation, that E1 and E2 are actually the same. And that means that if we calculate W1 being epsilon 1 E1 squared and W2 being epsilon 2 E2 squared, if we now calculate the ratio between these two energies, so for example W2 divided by W1, since E1 is equal to E2, this means that the ratio is just the ratio of the dielectric constants. That's going to be epsilon 2 divided by epsilon 1. And since epsilon 2, the constant of the rod, is actually the bigger one, this is going to be a number that's smaller than 1. And the larger the index contrast, the smaller this number is. So this means that the energy in the air is much smaller than the energy in the rod itself. So this leads to a situation where the electric field is very much confined in the rods. So here we have a situation of confinement. Good. So now we know what happens in case of TM polarization. Perhaps pause the video and try to do the same thing for TE polarization. TE is very similar but subtly different, of course. So for TE, or what we call TE in photonic crystal parlance, there we have the cross section here. So this is again our rod, but now the electric field is oriented like so. So we have E1 over there and E2 over here. Basic Maxwell theory tells us now that the normal component of the dielectric displacement, so dn, so that's the conserved quantity. So if dn is continuous, this means that d1 is going to be epsilon 1 E1 is going to be equal to epsilon 2 E2, because that's the definition of the displacement, right? So now, if we calculate the ratio of W2 to W1, that's going to be epsilon 2 E2 squared, epsilon 1 E1 squared. So this is going to be epsilon 2 over epsilon 1. But if we take the ratio E2 over E1, that's going to be E1 squared divided by E2 squared. Sorry, epsilon 1 squared divided by epsilon 2 squared. So now, in this case, the ratio flips. So if you just simplify this, and the ratio is actually epsilon 1 divided by epsilon 2. And in this case, it's not a number smaller than 1, but it's a number bigger than 1. So now we're no longer in a situation where the field is very much concentrated in the rods. Most of the field will actually be between the rods. So here we're dealing with an electric field which is not very confined. So let's call that unconfined. So based on these very simple arguments, this will allow you to draw some conclusions with respect to where the field will be mostly located depending on the polarization. So if the field is along the rods, most of the field will be concentrated there. If the polarization is in the other way, perpendicular to that, then we will have significant amounts of the field, of the energy present in the space between the rods.